I'd really like to welcome Dr. Bruno Basso. He's going to talk about a lot of the work he's been doing about soil stability maps to improve management for soil health and carbon markets. Dr. Basso is really internationally known presenter, expert, or researcher on spatial work and that like. So with that, I'm going to quit sharing and welcome Dr. Basso, and please start when you're ready. Thank you very much for joining us today.
Thank you very much, Paul and Leslie and the whole team invited me today. It's a pleasure to share with you some of my recent research carried out in the lab. And as Paul mentioned, I'll try to illustrate the meaning of this recent work about stability maps, how they relate to the soil health, and eventually touch upon a little bit about potential carbon sequestration and carbon markets. So it's well known that we are moving towards, or at least we hope to allow greater adoption of what we call regenerative practices, trying to move away from more conventional mono-successions and conventional tillages and so on, but rather see more diversity of crops, extended rotation, be able to use more recycling, and that now goes, there's a pretty new topic of research, circular economy, circularity, and regenerative nutrient cycles, compost. Where possible, is ideal to have animal integrated into the rotations with grazing forages and managing cropping residues. Cover crops and perennials play a critical role in building the soil health and stability of aggregates and soil organic carbon and so on. I will also touch upon precision conservation and the possibility of managing constantly low yielding areas with some alternative land use. And we all hope again to minimize disturbance to soils and use more advanced digital technologies. We need to place regenerative ag really at the center of the system that you may be aware of. The new some agencies like NIH, NSF, and USDA, and they talk about this concept of One Health, and so it's the healthy environment, healthy people, and healthy community. So, in more specifically, we want to see the regenerative agriculture contributing for healthy ecosystems, because the more we build resilient system through better carbon, better soil health, the lower are the losses of fertilizer from runoff and nitrate leaching, and because there's better, again, aggregate stability, water holding capacity. And so the loop goes around, better ecosystem, better healthy farmers, because if that is, if the farmers are play a critical role, and nowadays we know they are on a very thin margin from an economic point of view, and so be able to allow them to be on a good economic return and social well-being. The healthy ecosystem also allow to have more nutritious food, so more nutrient density because of the broader arrays of nutrients available through regenerative practices. And if the farmers again are healthy, we want to see, as is happening, more transparency on how food is produced, and so a healthy community by again having more of a consumer wellness, and be able to allow the possibility of anyone to purchase more regenerative products rather than seeing expensive prices. We just want to mention that we have a new center at Michigan State. It's a highly funded project, support $19 million by the FFR, the Foundation for Food and Agricultural Research. It's led by Jason Roundtree. He's a professor in animal science, and we have Michigan State, Colorado State, the Nobel Foundation, and many consumer package food company group from systems among some, Applegates, McDonald's, and several others who have contributed. As you know, the FFR requires a pretty strong matching funds. So digital agriculture is the core of the presentation today and has been around, even though I guess we have changed a little bit some of the names, but it isn't necessarily the same thing of precision agriculture, because normally with precision agriculture we really intend a more immediate connection to a variable rate application. In digital ag, it's the possibility of managing large amount of data coming in and using machine learning and AI and robotics and all kinds of development in the digital space. And so more recently I tend to use this more broader umbrella of technologies under digital agriculture. As you will see, some of the robotics even in applying water at basically for every single plant, or drones technology using for spraying or monitoring, or use of more sophisticated tools like thermal imagery and so on. So one of the things that people associate immediately with digital ag is, and again precision ag more specifically in this case, is the yield map. So a yield map, everyone knows that there is an extensive amount of variability in fields. It's the norm rather than the exception. And so what you're seeing here, this is about 60-acre field in Michigan, pretty rolly terrain as in many places. And you'll see that it would be very difficult for a farmer to implement a variable rate immediately just by looking at this spatial map fluctuating. And so the question that has really driven my research is like, how much does this spatial pattern repeat over time, or which areas are constantly behaving in one way versus others that they go from high to low and so on. And so from that, by integrating this 10-15 years of yield maps changing from high to low yielding and again the unstable, we came up with this concept that has been around already, published 20 years ago about it, and other researchers as well. So the areas that you see high and stable are intended as a qualitative description of areas being always performing well, always higher yield, despite the fact of a lower yielding. They always do better than the rest of the field. Medium and low and stable, same thing. Low and stable, they constantly underperform. They constantly, in the case of corn, we have seen that they are in the 120, 130 bushels versus an average of 170 and so on. So they are drastically different, significantly different between each other. And then there are areas that they vary from one year to the next, and so those are called the unstable. Even though we have a lot of yield maps, and you'll see in a minute, and even available to farmers, 68% of the U.S. corn is harvested with combines, but only 45% of the other, which is still a very large area. And a lot of the companies that provide the service have the availability to this data. But I wanted to make this concept scalable, and so by integrating this with imagery, I wanted to see how much we could use the yield mapping that we had, the maps that we have, to validate with the process using remote sensing. So you'll see that in a minute. These are the availability of in-house of yield maps, and some of them, as you see, many that have been around for large data sets for me, and 182 fields with more than 10 years of data. So very good distribution, and because of that, we have really been able to learn how this spatial and temporal variability really occurs in the Midwest. Before I move into the scalable approach, another concept, again, with the same exact type of analysis, is we've been start using thermal imagery. Thermal is it's a proxy for the availability of water. So it's really more, in a very simple term, if a plant or a field, plants run fever, are they hotter than normal and then to the neighbor? And so this integration of thermal imagery allowed us to understand areas that, as you'll see, like they're more like on a mirror image, the areas where they are cold and stable, cold being available water is sufficient to satisfy the evaporative demand, and so plants transpiring are always colder than plants where they shut down the stomata and not be able to transpire, so they get hot. And so they match very much the yield stability map, and it was very positive. We have again an extensive analysis going on, and soon hopefully be able to publish this paper about the importance of using thermal imagery, not just for ET, but also we'll start using it to detect the presence of diseases for the same exact principle of planting shut it down in the presence of a stressor. And ultimately, we're integrating them in this new concept of plant health stability. So where you could have yield, thermal stability, optical analysis when DVI. And so this allows you to really separate the areas where what are the limiting factors? Is it more really driven by water, or is it more driven by nutrients, by looking at the spatial pattern of the maps that you see here, both yield, thermal, or NDVI. Now, this is pretty impressive. I mean, I can never be, even though I've been in this field for over 25 years or so in using remote sensing, and these are 900 images that you're seeing here every single day, 3 meters on the ground. And so you can capture just about anything from satellite. Now, you have to be sophisticated, and often to me, that's the biggest gap, how we integrate. And the lab really does this sorts of work. And by being able to capture this spatial and temporal variability, over time, this is what we use to develop the yield stability map for the entire landscape. And so we have been able to do this for every single common land unit for any field of any farmers growing corn and soybeans. The map has been extended to other states, so including Nebraska, Kansas, and we have developed a yield stability map from satellite imagery in Argentina, Brazil, Europe, Australia. And so it's a concept that is extremely solid because it uses the plants as indicators of the variability. So now you can basically click on any of these fields and be able to get the yield stability map. Now, to give you a little bit of what we found across the US Midwest of the 80 million acres, it was an amazing strong signal that the numbers have a very low standard deviation, but on average 48% of the within field variability, it's constantly producing high yield with a nitrogen use efficiency doing the mass balance of 75%, which is, we have in agriculture, we are in soils, we are in a leaky system. You can't ever stop leaching. That's part of the drainage. I mean, nitrates move with water, but if they're used by the plants efficiently and the conditions of, again, the soil health of these areas supposedly could be better, you'll see that in a minute. And so 75% is a good number for nitrogen sufficient, extremely high compared to a 30% on a global, but the low and stable areas are close to that low number. So 45% ends up in the plant and the rest is lost. 27% have about 58s, with the fluctuation of being much more towards the high yielding versus low yielding. And without going in details, but pretty strong impact on economics, energy, the food and energy water nexus here integrated with CO2 emitted for only the analysis of the fertilizer that was not used by the plant. What we also learned over the years and published is that for each of these fields, we have a knowledge of the vulnerability or the causes of which areas tend to be more, again, vulnerable to water deficit versus more prone to have water accumulating based on the digital elevation model and terrain attributes, we know which one have excess water over deficit, and which is a useful layer to make additional analysis of these fields. So one of the things that we wanted to ask is a research project that I started recently by basically investing some of the money that I had available, and it was, let's see a very thorough, detailed sampling across this transect of farms, large farms of different conventional tillage and no tillage, and cover crop, no cover crop, and different soil types, and sampling across using yield stability maps to be able to see what is the status of soil health, and what is the relation with soil carbon. So that's very much what you would like to hear. I mean, a legitimate question. Is there any relationship to that? And so first of all, we see that soil organic carbon is significantly lower in low and stable areas, and very visible compared to the high and stable and medium and stable in between. The unstable areas, as you see, is similar to the medium or the high, because high and unstable doesn't mean low. It means potentially you can be always on a high trajectory, I mean on high yielding, but then 1 year something happens that you can be flooded. So it's something that you want to look for these areas of instability, but they may have a tendency to be good yields. And so those are the areas that they are either affected by too much water or too little water. And in fact, they either happen on depressions. And so unless you flood, the depressions will always give a pretty good, high yielding because of the water availability. But if they get excessive amount of rain, as we've shown in the papers we published, then they become unstable. They are the one giving you the lowest yields. The low and stable areas, it was interesting also to find that they are the ones with the only zones that they have changes in bulk density. So the lower layer, the 6 to 12, it's more compacted. And so that was an indication, because you could ask, what are the reasons of the low and stable areas, which there are multiple. It's not often people say, yeah, they tend to be on the edges of the field, but they can be because of the wildlife. Wildlife obviously pulls you down, your yield down, but it's much more in the 25 to 30% reduction. We could verify that wildlife wasn't necessarily the driver of the low and stable zones, because monitoring throughout the season, we saw that the vegetation indices of the plants growing on the edges of the field before even the cob came out was lower compared to the rest of the fields. And so one of the things that we've been doing over these farms is running this integrated test of soil fertility that is developed by the Woods End Laboratory, and we've been using it because we really believe in a system approach and be able to quantify. So for each of these fields, they are categorized based on soil series using the climate, the soil orders, and so on. So this odometer is separated in overall fertility. So it's very important to know if you have an overall soil health score, is it due to biology or also some of additional fertility scores. And so those are separated. And so we ran on some of these fields, and you can see the numbers being significantly different between the low and stable zones and the high and stable zone, with the high and stable zone always having a greater soil health score. And that's pretty much what we would expect, in the sense that if you have a high yielding areas, the amount of residues and roots you produce, a healthy plant, the amount of biomass and carbon that you return is always greater compared to an area that has more soil exposed because of low areas. So we're able to monitor this system both with remote sensing as well as this is with a modeling system. You can see the areas in green are example of fields that are predominantly in the high and stable zones, but you have low and stable zones where they are, and so we can learn the variations and run scenarios. What if I change something, and see what we have. And the instability is separated in unstable depression areas, which you see they have lots of green and high yielding, but they're also unstable in hilltop. They most likely run out of water, and unstable slope, same way, they basically have water running down. Converting this analysis into profitability, and you probably are aware of this, but there is a good chunk of the fields where farmers are currently losing money. And they are often aware of that sometimes they don't even know details much about cost of production. And but even though they know they have a thin margin, and so the possibility of doing something else on these areas, especially when you know that you're losing over $100 or $200 per acre on those areas, is going to be critical in the future for farmers. And so the profitability the profit stability, it's another concept. Everything is because you have to account for spatial and temporal variation of this variable. You can have 1 year that you made more money, but is it something that you rely just on that particular year? Let's look over a integration of the years. And so this is the example right there. The top map is a corn map into 2016, and converting this is very detailed with the cost of production that it was shared by the farmer for every single thing, the expenses and sales and so on. So basically the farmers lost close to $150 on those red areas. But when you link the stability map of 11 years in the profit stability of 7 years of corn, then you have this knowledge of basically the losses of the dark red are high, and they are again in the 200, and some of the areas that they are unstable. So this would change the long-term analysis of fields, in addition to be able to assess the quality of the land in terms of rental prices. And we're getting, no one would buy necessarily a piece of land like a car, not knowing how many kilometers has done, and what happened if everything. We buy a house, we do an inspection, we have a possibility through this system that these fields can be quantified in terms of spatial and temporal variability based on these observations, and not just modeling but true observation. So for each field, we know where those low and stable areas are located, with very strong validation from the yield maps, because that's the strength of this analysis. You can use remote sensing, but you just don't project. This is done for every single field. And so this is an example of zooming in these fields, and we quantify again in this paper that we're working currently, that there are 23 million acres for the analysis, the areas that we looked at it, and of low productivity. Where they are located, are they in the middle of the field or at the edge of the field? And are they greater than 1 acre or lower than 1 acre? Are they contiguous or not? So very valuable information for both the farmers or anyone working in this space. And so managing for low and stable areas, you could reduce nitrate leaching, greenhouse gas emissions, because you wouldn't be putting excessive amount of fertilizer in an area that is giving you 120 bushels. Ideally, you shouldn't. And soil carbon sequestration could be increased by using different plants necessarily, and not. But again, bringing biodiversity if those areas were to be planted with something else. And so that's the, again, concept of precision conservation, even though it's been around more as a general term of using, conserving resources. This is more of a really procedure or protocol where you would go from having a profit stability map, identifying the areas where we know there is a response to variable rate and optimal fertilizer. We still need to continue production and boost the yields and increasing the yield, and so those are the areas that you have greater fate of doing well, and so you have optimal fertilizer. No fertilizer, you wouldn't put fertilizer again in the low and stable zones. But we're trying to increase biodiversity, and you've probably seen the government current administration is pushing for this 30 by 30, eliminating unproductive, focusing again more on expanding CRP as well as increasing conservation land. And so this is an opportunity for farmers rather than a threat, because they can be paid. And we actually have a project that I'll describe in a minute, incentivizing farmers to plant, which they can be biodiversity crop, they can be hay, or they can be native pollinators, and so they can actually make money by receiving incentives, as well as potentially, if they adopt to go into the carbon markets, there is quite a bit of carbon sequestration going on with perennial roots and biomass, and as you see with the map on the right. So this is a project funded by the NRCS, the CIG, the Conservation Innovation Grants, where we received a big chunk of the funding goes to farmers to be able to do two things: either variable rate application in-season side dressing, rather than putting fertilizer all at the beginning of the season or in the fall and so on. And so the other is precision conservation. Be able to be willing to allocate some of the areas that will not be, they've been shown not to be productive. And so we developed this algorithm that every farmer that has participated on their farms Some of them have given us quite a bit of acreage, and so these are the areas that they are going to be. Some of them have already planted biodiversity, native vegetation, or different kind of mixes, and they are actually paid from through this grant. But it's the beginning of a potential, policy, because again, it doesn't really make much sense to continue to put 180 or 200 pounds of N in areas where they don't return the benefit. And just to go towards the end here, we use stability map also because of this strong understanding of the dynamics, spatial and temporal. We deliver prescription maps to farmers based on stability map, again with the idea of reducing amount on low and stable zones. And I know farmers manage for a perfect year, but this has shown that perfect year on that zone, you may have already reached it, and it wasn't with the input that you provided. Because if you continue to harvest a low yielding, you know that it's like you giving a greater amount of food to someone that just does not have a big stomach, and so you obviously will be wasted. And so the graphic here shows what the mapping and the prescription that we give to the farmers as an example, and the benefits of not affecting yield but increasing nitrogen use efficiency and reduction of nitrates. We're also embarking in this is a project that was funded by the Corn Growers Association of Michigan, where we wanted to show them that there is an opportunity of analyzing the as applied map as a result of the variable rate, and as a reference compared to the high and stable zones, there is the amount of fertilizer that is being saved. So the area here where you see 50 is what was an amount applied, and because the maximum was 160, you see that wherever they saved 110 kilograms or pounds per acre, they're similar. And that can be converted into how much CO2 equivalent has been reduced in the form of N2O, even using tier 3 examples of N2O emissions. And so, but if you were to use precision conservation, not even putting 50 but using 0, then you'll see that in those areas you save 160, which is about 500 kgs of CO2 equivalent per hectare, which is even more than what a very good cover crop basically gives. So in conclusion, I wanted to point out that we described this in an invited paper that is published and available, open to Nature Sustainability, where we believe that the possibility of using and analyzing big data, sensors, robotics, yield mapping, AI, analysis of cost, benefit, profit, linking them into farm level tools where again the stability sits at the middle, and to then provide analysis for either profit or variable rate or enhancing bioenergy, biodiversity. You've seen the possibility of scalability and analyzing trade-offs, and with the ultimate goal of either design policy that will help farmers adopt more regenerative practices, build the soil health that is needed to make the system much more resilient to increased variability in climate. And with that, obviously this work not possible without the work of a group of students and staff that they work in my lab, and the funding sources very broad of different kinds, but they seem all have an interest, whether it's soil health or technologies or sustainability or circularity. So, but without them, this work is not possible. So thank you very much for your attention.